Okay, on the bench today is a prototype of an analog computer that I built. I really don't know entirely what I'm doing, so I'm just building one the way I think it should be built. I have incoming power here. There's a little switching power supply here that will take 5 volts and convert it to plus and minus 15 at 30 some odd milliamps to power all of these op amps. And they are not LT 1012s, they are TLO 51s. I went with a cheaper option that's almost as good anyway. So I have each of the sections. I have 3 integrators, and I have these dip switches that will select different capacitors to select different frequency ranges, because usually these integrators and differentiators are only good for a certain frequency range, and so you have to select what that is and then roll with it. I have a multiplier here. I think it only works for certain voltage ranges, but it is a multiplier. It's a hell of a lot cheaper than a multiplier chip, so I went with it. Not sure how useful it's going to be. I have here buffers and inverters. I got inverters and buffers here to help with that. Sometimes you need those. I have a bank of attenuators here, literally just 100K potentiometers. Audio pots. I'm not sure if I should have gone linear or audio. I got audio. And I have 2 amplifiers here that have adjustable gain. And these sockets are just sort of input and output to each thing. I have little common bars here. And I have 3 mixers and a subtractor or a difference amplifier. And I tried to label all them with the silk screen, and I did a decent job. There's some small issues with this PCB. It's not perfect. Like this, the fitment of these capacitors is not quite right. A lot of the fitment of the components is just a little off. Some of the silk screen's not quite right, but it functions. I had to make a couple of modifications on these amplifiers. They were not built correctly, so I had to cut and wire a trace. Fairly typical of a prototype, at least my prototypes. So I'll show you what this thing can do. I haven't done a whole lot with it, but I'll show you what just like a basic second order linear ordinary differential equation looks like. I'm also not a mathematician or a computer scientist, so forgive me if I make any errors in my speech about these things. Okay, so this analog computer is wired up to compute this equation here, this differential equation. The second derivative of x with respect to t is equal to negative 1/2 of the derivative of x with respect to t minus x plus 4, or in that other form there with the dots. So we have different components on here. This isn't all of them, but this is the ones we will be using to render this equation. We got 2 integrators, inverter and non-inverting amplifier, which actually we won't really use, and then an inverting summer. All the summers are inverting on this board. So for the entire system, we basically have 2 integrators. The initial conditions will be set to 0 by these reset buttons. And we have an inverter and basically an attenuator going to a summer. We have negative 4 volts, which is that plus 4 in that equation, which is an inverting summer. So all the polarities that go in have to be reversed. And of course, the output of x minus x gets added to the sum, adding all that together to get that. Now, if we put this equation in Wolfram Alpha, you get a solution that's supposed to look a little bit like this. Now on this analog computer, we are going to set up the coefficients with the coefficient negative 1/2 with these potentiometers. It's going to be hard to do that. These are logarithmic and it won't be exact. but it'll give us the idea of the behavior of this equation. Now, the constant 4 is set by this power supply here, and that's going in. It's actually going in through another attenuator, so we can also vary that with ease if we want to. And I'll show you what it looks like on the scope. So here's what the coefficient, the constant actually at 4 volts. If I drop that down with the attenuator back to 0, or it should be, let me actually adjust that. Should be right on the 0 mark. And right now it's on 2 volts per division. So now that we've raised up 4 volts, it goes up 2 divisions. And then if I hit the reset button on one of the integrators, we get a waveform. Now to see that waveform more clearly, we're going to have to decrease the time base. Increase maybe slightly. You can kind of see there, if I turn it on normal triggering here, you can kind of see that. To get that waveform to start, all I'm doing is hitting that reset button right there. There's reset buttons on each of the differentiators and each of the 3 integrators. So when I press that, I can get the waveform. It looks a lot like what Wolfram Alpha said it would look like. Now if I play with that coefficient a little bit, if I increase that coefficient, or decrease that coefficient, get it closer to 1. If that coefficient approaches 1, we get sort of a damped oscillation that just gets more and more damped. And as we increase that, or decrease rather, get it closer to 0, that fraction gets larger. It gets less and less damped until it rings, or max it out, rings almost indefinitely. Bring the time base way out to see that better. So that's with it pretty close to 0. And if you were to make that coefficient positive, you would get this. Let's play with the time base. Now our amplitude is way the heck up there. We're actually clipping, matter of fact. If I bring that down a little bit, we're clipping a lot actually. If I bring that down, bring it closer to 1, see that the waveform kind of just increases until it clips, or it sort of decays down to nothing very slowly. So we can see very well the behavior of this equation by playing around with the coefficients in real time with this analog computer. And right now I'm playing with the constant 4, that's closer to 0. If we raise it up, obviously the output changes. Now interestingly, if I bring that coefficient down to 0, or that constant down to 0, the equation doesn't always start when the coefficient minus 1/2 is negative. I'm going to go through the schematic of this analog computer. So go into, well, I'll show you the power supply first. It's pretty simple. I literally just took a standalone chip, and I just have a power jack and a couple of capacitors. And the way I built the integrators was, well, I built everything so that there would be decoupling caps next to each section, and there would be a connector, or a ribbon cable thing so you can plug in individual wires and connect each section. But I have 3 integrators, TLO 51s, and I have a dip switch, a 5-position dip switch to switch in different value capacitors for different frequency responses. I haven't moved these labels, so they're all buried, unfortunately. But I also have a 1 meg resistor to switch in. Sometimes the integrator can have problems if charge accumulates and doesn't like discharge. It's weird. Like if you put a continuously variable signal into it, it may drift or it may just not work. Although I found for this video, I didn't actually need this at all. This probably could be 10 mega ohms. I don't know if it really matters. I don't know what this value should be. I have this reset button on each section, enabling you to basically kill the charge on any of these capacitors. So you can reset the entire circuit or just that one part of it back to zero, back to what t equals 0 would be in an equation, or close enough anyway for most things. And the differentiator is very similar, except it's switching a bank of resistors to get your different frequency ranges. And I tried to make these spaced so that it was sort of logarithmic, so you'd have frequency ranges that are usable, and they're just not all on top of each other basically. And again, you have the reset buttons shorting out the capacitor there. These are all film capacitors, by the way, so they don't leak. Or if you have to plug in some kind of signal and have it acquire some sort of signal, you want it to stay there and not discharge. Yeah, generally the higher the capacitance, the lower the frequency. Now, so I got inverters and buffers, and so yeah, just literally pretty simple inverters, buffers, gain of just 1. I've got a bank of attenuators and attenuator amplifiers, basically. Just a non-inverting amplifier with variable gain. Well, really, it's just an amp, so it's gain from anywhere from 1, 2, up to like 100 or something, thereabouts. It's a usable amount of gain, basically. So I've got the mixers. I have 3 mixers and 1 difference amplifier, a subtractor, they call it. And there's only 2 inputs on the subtractor, but I don't imagine I'll be using it that much. There's a couple of stages in here I'm not sure I'll end up using that much, but it's worth having, I think, just to mess around with. And the subtractor is one of them. All unity gain, of course. And there's also a multiplier, which I didn't know you could make a multiplier out of just regular op amps, but apparently you can. You have a couple of logarithmic or exponential amplifiers and logarithmic amplifiers, because I guess that nonlinear process enables you to mix those together, and that mixing together of the nonlinear amplification is multiplication, I guess. It's some form of multiplication, and then you turn it back into a normal signal. Very, very clever, very interesting, although I'm not entirely sure it works for all signal levels. It works for certain signal levels. I'm not even sure if these resistors are the correct value. I'll have to play around with that. Yeah, that's really all there is to it. I chose the TLO51 op amp because it's cheap, and I got some common terminals here, and I usually basically use these for ground. See, like I said, I don't really know what the hell I'm doing, so I'm just building this the way I thought it should be built.